Welcome to Learning Chemistry with Faye. In this video, we're going to learn how to determine energy and enthalpy in a lab setting with the endothermic and exothermic reactions. Let's start with what is energy. There are two forms of energy: heat and work. In a reaction, we're dealing with pretty exclusively just heat. Since we're not changing pressure or changing volumes to our reaction, so we can eliminate this work variable. So with heat, we're usually talking about direct heat form, like a fire, or sometimes it's a light source. So they're all can be applied to your reaction. So how do we usually start with the experiment? We usually start with an enclosed container, right? So this is some kind of foam insulated cup to keep all the heat inside. And you have some kind of a measuring device here. In our case, it would be the temperature probe. Here are your solvents. And this is where all your reaction occurs. So you can picture this reaction as an entity. Okay, although the reaction usually occurs homogeneously through your solution, but here you could, just for the sake of visualization, we're going to think of this as an entity. And this can be you can think of it as a subject, and we call it the system. Okay, the rest of it is your solution. And if you think about it, what is in your solution? Your solution, majority of your solution are just water, right? So in this system where your reaction occurs, you treat it as two entities. Okay, so this one is your reaction. Here is the rest of your solvent. And your solvent is absorbing all the energy coming from the reaction. So if your reaction is giving energy, it's directly given to your solution, right? So if your energy right here, if your reaction giving energy, and if it's a positive energy, then it's all going to be transferred into the solution. So if your solution has a temperature change, from a lower temperature to a higher temperature, then you have something called exothermic reaction. That means your reaction occurs spontaneously as the reactants meet, and is going to release energy into your solution. If you think about it, if this is a closed container, right? All the energy has to be in here. Whatever the energy that the reaction is releasing all has to be absorbed by the solution. So that means whatever the energy that you are monitoring inside the solution is going to be the exact opposite of what's released from your reaction, right? So if the if your reaction is going to take energy from your solution, which means now your reaction is no longer spontaneous unless there's some kind of energy is given to it. It's going to take it from your solution, right? So that means these two forms, if your energy is measured for your solution, in this case we call it Q solution, it's going to be positive, which means it's taking energy from the reaction. That means it's the same amount of the reaction, same amount of energy is taken from your reaction. Okay, and whenever your reaction is releasing energy into the solvents, into your solution, we call that exothermic. And whenever it takes energy from your solution, We call that endothermic. So over here, I'll write it more clearly. We're going to have heat of solution equals to negative heat of reaction. Okay, so how do we calculate? So the first thing that you want to calculate is to determine the heat of solution. How do we do that? In order to determine the heat of solution, we start with mc delta T. With M, this is the mass of everything in your solution. This includes your solvents, all your reactants, and anything else that's currently in that enclosed system. Everything. So this is a weight. It should be measured in grams. And also you have C, which means the heat capacity. What is heat capacity? Heat capacity means the capacity of the amount of heat that a substance can hold. So every single substance can kind of absorb heat and hang on to it, right? So this heat capacity shows basically the amount of energy that's measured in joules per gram per Celsius that a particular substance can hang on to it. And they're all different. For example, same amount of gold is going to have a different heat capacity or the ability to hang on to heat than a gram of water, right? So majority of the time that our experiment uses solvents as water. And if you notice, most of your reactions inside a solution are just water. We can apply this as the heat capacity of water, which is 4.184 joules per gram per Celsius. And here you have delta T, which is change in temperature. Remember, change in temperature is always T final minus T initial. So whenever you have a change in something, you represent it with a delta. And if you have a delta T, you always use the final form to subtract the initial. If that's delta V, then it's final volume minus initial volume. If it's delta P, then you have final pressure subtracting initial pressure. So in here we have mass multiplied by the heat capacity multiplied by the temperature change. And this will give you the energy, the heat, right? The heat of solution in the energy form, right? This is the only energy that you're going to calculate for your reaction. First, you need to determine this heat of solution. So once you have your heat of solution, you can determine the heat of a reaction by using heat of solution equals to the negative of heat of reaction. So as we remember, any energy that is absorbed by the solution is given from the reaction, or vice versa. And once we determine the heat of reaction, we can move on to determine the enthalpy. In order to determine enthalpy, we need to start with a balanced chemical equation. If you don't have a balanced chemical equation, you won't be able to determine the enthalpy of reaction correctly. Okay, so first, you always need a balanced chemical equation. Let's give an example. Let's just say we have a reaction with the two reactants, give two products. This can occur in different formats. You can have three products. Sometimes you can have three reactants with one product. But in our case, we're just saying there are two reactants to generate two products, to form two products. And one of the reactants, you're going to need 2 moles of one reactant with 1 mole of another reactant to form this product. So what you need to do next, first, you need to find the limiting reagent. How do we find the limiting reagent? You are going to either use a weighted out weight. So this should come from your direct analytical balance. In correct sig figs, right? Divide by the molecular weight of this reactant. And this will give you the moles of A. Since you need 2 moles of A in this particular reaction, remember, if you wanted to determine the limiting reagent, you need to divide this by 2. Okay, and then you do the same as the other reactant, the weight of your reactant. If the weight of the other reactant, if the weight of this reactant is not available and they came from a solution, you need to remember that you need to calculate the very specific amount of just this reactant. So make sure you don't use the weight of the entire solution, but just the reactant weight. That you can calculate it from a concentration, which is usually expressed in molarity. Molarity also equals to moles per liter. So whenever you wanted to convert a concentration into a weight of your reactant, you can't really use this big letter M because there is no way for you to convert it. So what you wanted to do, you wanted to automatically write this M into a mole per liter format. So for example, if you have something that's 1.0 molar, you write it as 1.0 moles per liter. And this should look a lot more familiar and very easy to read. Right? So once you have this, you're going to convert this number into milliliters or into moles with the correct milliliters of the solvents that you used. So in this case, you wanted to do 1 liter over 1,000 milliliters. Right, so this is your first conversion since all your measurements of your solvents or solutions are measured in milliliters. And how many ever milliliter of the solvents that you used. And once you use this particular equation, you will get the mole number of your reactant B. Remember, whenever you're comparing the reactants or comparing the quantity of your products, you can never compare in weight. You can never be comparing from grams to grams. It's like, oh, I saw this has less grams. It really depends on the molecular formula, depends on the weight of your particular compound. It depends on how many moles per reaction the reactant will need. So remember, never assume and never compare your reactants from weight to weight. You always have to convert it into the moles. So over here, you will be able to calculate a mole number of A, your first reactant, and the mole numbers of your second reactant. And then you will simply just pick whichever the mole number that's smaller. Okay, the smaller mole number is your limiting reagent. For example, if you are making apple pie and you have so much dough and so much apple, you have unlimited amount of apples just because you have an apple tree, but you only have 10 pounds of dough. What is the limiting reagent? Your limiting reagent is going to be the one that's whichever can run out first, which in this case is whichever has the smaller mole number. That would be your limiting reagent. Once you have your limiting reagent, you will be able to use the heat of reaction that you calculated earlier and divide by the mole number of your limiting reagent. And this gives you the enthalpy, which is represented by delta H. Hopefully this will help you with your endothermic and exothermic reactions. And feel free to reach out to me with any questions in the comments.